Understanding ownership. Ownership is Rust's most unique feature, and it enables Rust to make memory-safe guarantees without needing a garbage collector. Therefore, it's important to understand how ownership works. In this chapter, we'll talk about ownership as well as several related features, borrowing, slices, and how Rust lays out data in memory. What is ownership? Rust's central feature is ownership. Although the feature is straightforward to explain, it has deep implications for the rest of the language. All programs have to manage the way they use a computer's memory while running. Some languages have garbage collection that constantly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks at compile time. None of the ownership features slow down your program while it's running. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is the more experienced you become with Rust and the rules of the ownership system, the more you'll be able to naturally develop code that is safe and efficient. Keep at it. When you understand ownership, you'll have a solid foundation for understanding the features that make Rust unique. In this chapter, you'll learn ownership by working through several examples that focus on a variety of common data structure, strings. The stack and the heap. In many programming languages, you don't have to think about the stack and the heap very often. But in a system programming language like Rust, whether a value is on the stack or the heap has more of an effect on how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter, so here's a brief explanation in preparation. Both the stack and the heap are parts of memory that are available to your code to use at runtime. But they are structured in different ways. The stack stores values in the order it gets them and removes the values in an opposite order. This is referred to as last in, first out. Think of a stack of plates. When you add more plates, you put them on top of the pile, and when you need a plate, you take off the top. Adding or removing plates from the middle or the bottom wouldn't work as well. Adding data is called pushing onto the stack, and removing data is popping off the stack. All data stored on the stack must have a known fixed size. Data with unknown size at compile time or a size that might change must be stored on the heap instead. The heap is less organized. When you put data on the heap, you must request a certain amount of space. The operating system finds an empty spot in the heap that is big enough, marks it as being used in, and returns a pointer, which is the address of that location. This process is called allocating on the heap and is sometimes abbreviated as just allocating. Pushing values onto the stack is not considered allocating because the pointer is a known fixed size and you can store a pointer on the stack. But when you want the actual data, you must follow the pointer. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the staff finds an empty table that fits everyone and leads you there. If someone in your group comes in late, they can ask for where you've been seated to find you. Pushing the stack is faster than allocating on the heap because the operating system never has to search for a place to store new data. That location is always at the top of the stack. Comparatively, allocating space on a heap requires more work because the operating system must find a big enough space to hold the data and then perform bookkeeping to prepare for the next allocation. Accessing data in a heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporarily, processors are faster if they jump around less in memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all orders at one table before moving on to the next table. Taking an order at table A and then an order from table B and then one from A again and then one from B again would be a much slower process. By the same token, a processor can do its job better if it works on data that's close to other data, as in the stack, rather than further away, as it can be on a heap. Allocating a large amount of space on the heap can also take time. When your code calls a function, the values passed into the function, including potentially pointers to the data on the heap, and the function's local variables get pushed onto the stack. When the function is over, these values get popped off the stack. Keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often. But knowing that managing heap data is why ownership exists can help explain why it works the way it does. Ownership rules. First, let's take a look at the ownership rules. Keep these rules in mind as we work through the examples that illustrate them. Each value in Rust has a variable that's called its owner. There can only be one owner at a time. When the owner goes out of scope, the value would be dropped. Variable scope. We've walked through an example of a Rust program already in Chapter 2. Now that we're past basic syntax, we won't include all the function main code examples. So if you're following along, you'll have to put the following examples inside a main function manually. As a result, our examples will be a bit more concise, letting us focus on the actual detail rather than boilerplate code. As the first example of ownership, we'll look at the scope of some variables. A scope is a range within a program for which an item is valid. Let's say we have a variable that looks like this. The variable s refers to a string literal, where the value of string is hard-coded onto the text of the program. The variable is valid from the point at which it is declared until the end of the current scope. Listing 4-1 comments annotating where the variable s is valid. Listing 4-1, a variable and the scope in which it is valid. In other words, there are two important points in time here. When S comes into scope, it is valid. It remains valid until it goes out of scope. At this point, the relationship between scope and when variables are valid is similar to that in other programming languages. Now we'll build on top of this understanding by introducing the string type. The string type. To illustrate the rules of ownership, we need a data type that is more complex than the ones we've covered in the data type section of Chapter 3. The type covered previously are all stored on the stack and popped off the stack when their scope is over, but we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data. We'll use string as the example here and concentrate on the parts of the string that relate to ownership. These aspects also apply to other complex data types, whether they are provided by the standard library or created by you. We'll discuss string in more depth in Chapter 8. We've already seen string literals, where a string value is hard-coded into a program. String literals are convenient, but they aren't suitable for every situation in which you may want to use text. One reason is that they're immutable. Another is that not every string value can be known when it writes our code. For example, what if we want to take user input and store it? For these situations, Rust has a second string type, string. This type is allocated on the heap and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function like so. The double colon is an operator that allows us to namespace a particular from function under the string type rather than using some sort of name like string underscore from. We'll discuss syntax more in the method syntax section of Chapter 5. And when we talk about namespacing with modules and paths for returning to an item in the module tree in Chapter 7. This kind of string can be mutated. So what's the difference here? Why can string be mutated but literals cannot? The difference is how these two types deal with memory and allocation. In the case of string literal, we know the contents at compile time, so the text is hard-coded directly into the final executable. This is why string literals are fast and efficient, but these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory onto the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. With the string type, the order to support a mutable, growable piece of text, we need to allocate an amount of memory on the heap, known at compile time, to hold the contents. This means the memory must be requested from the operating system at runtime, and we may need a way of returning this memory to the operating system when we're done with our string. That first part is done by us. We call string from its implementation requests the memory it needs. This is pretty much universal in programming languages. However, the second part is different. In languages with a garbage collector, GC, the GC keeps track of and cleans up memory that isn't being used anymore. We don't need to think about it. Without a GC, it's our responsibility to identify when a memory is no longer being used and call code to explicitly return it, just as we did to request it. Doing this correctly has historically been difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from listing 4-1 using a string instead of a string literal. There is a natural point at which we can return the memory our string needs to the operating system. When S goes out of scope, when a variable goes out of a scope, Rust calls a special function for us. This function is called drop, and it's where the author of the string can put the code to return the memory. Rust calls drop automatically at the closing curly bracket. Note, in C++, this pattern of deallocating resources at the end of the item's lifetime is sometimes called resource acquisition in initialization, RAII. The drop function in Rust will be familiar to you if you've used RAII patterns. This pattern has a profound impact on the way Rust is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we've allocated on the heap. Let's explore some of these situations now. Ways variables and data interact. Move. Multiple variables can interact with the same data in different ways. In Rust, let's look at an example using an integer in listing 4-2. Listing 4-2 assigning the integer value of variable x to y. We can probably guess what this is doing. Bind the value 5 to x and then make a copy of the value in x to bind it to y. We have two variables x and y, and both equal 5. This is indeed what is happening. Because integers are simple values with known fixed sizes, these two 5 values are pushed onto the stack. Now let's look at the string version. This looks very similar to the previous code, so we might assume that the way it works would be the same. That is, the second line would make a copy of the value in S1 and bind it to S2. But this isn't quite what happens. Take a look at figure 4.1 to see what is happening to string under the covers. A string is made up of 3 parts shown on the left. A pointer to point to memory that holds the constant of the string, a length, and a capacity. The group of data is stored on the stack. On the right is the memory on the heap that holds the contents. Figure 4.1 representation in memory of a string holding a value hello bound to S1. The length is how much memory in bytes the contents of the string is currently being used. The capacity is the total amount of memory in bytes that the string has received from the operating system. The difference between length and capacity matters, but not in this context, so for now it's fine to ignore this capacity. We assign S1 to S2. The string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In other words, the data representation in the memory looks like figure 4-2. Figure 4-2, representation in memory of variables S2 that has a copy of the pointer, length, and capacity of S1. The representation does not look like figure 4-3, which is what the memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation S2 would equal S1 could be very expensive in terms of running performance if the data on the heap were large. Figure 4-3, another possibility for what S2 equals F1 might do if Rust copied the heap data as well. Earlier we said that when a value goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for the variable. But figure 4-2 shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as double free error, and it is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, there is one more detail to what happens in this situation in Rust. Instead of trying to copy the allocated memory, Rust considers S1 to no longer be valid, and therefore Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. You'll get an error like this one because Rust prevents you from using the invalid reference. If you heard the term shallow copy and deep copy while working with other languages, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable instead of being called shallow copy, it's known as a move. For example, we would say that S1 was moved into S2. So what actually happens is what's shown in figure 4-4. Representation in memory after S1 has been invalidated. Figure 4-4. That solves our problem with only S2 valid. When it goes out of scope, it alone will free the memory and we're done. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Ways variables and data interact. Clone. If we do want to deeply copy the heap data of the string, not just the stack data, we can use a method called clone. We'll discuss method syntax in Chapter 5, but because methods are a common feature in many programming languages, you've probably seen them before. Here's an example of a clone method in action. This works just fine and explicitly produces the behavior shown in figure 4-3, where the heap data does get copied. When you see a call to a clone, you know that some arbitrary code is being executed and that the code may be expensive. It's a visual indicator that something different is going on. Stack only data, copy. There's another wrinkle we haven't talked about yet. This code using integers, part of which shown in listing 4-2 works, is invalid. Oh, wait, valid. Okay, why aren't you highlighting? There we go. But this code seems to contradict what we just learned. We don't have to call to clone, but X is still valid and wasn't moved into Y. The reason is that the types such as integers that have a known size at compile time are stored entirely on the stack. So copies of the actual values are quick to make. That means there's no reason why we'd want to prevent X from being valid after we create the variable Y. In other words, there are no differences between deep and shallow copying here. So calling clone wouldn't do anything different from the usual shallow copy, and we can leave it out. Rust has a special annotation called the copy trait that we can place on types like integers that are stored on the stack. We'll talk more about traits in Chapter 10. If a type has the copy trait, an older variable is still used after assignment. Rust won't let us annotate a type with the copy trait if the type or any of its parts have implemented the drop trait. If the type needs something special to happen when the value goes out of scope, we can add the copy notation to the type. We'll get a compile time error. To learn more about how to add the copy annotation to your type, see derivable traits in Appendix C. So what types are copy? You can check the documentation for a given type to be sure, but it's a general rule. Any group or simple scalar value can be copy, and nothing that requires allocation or some form of resource is copy. There are some types that are copy. All integer types such as U32, the Boolean type bool with values true and false, all the floating point types such as F64, the character type char, tuples if they only certain types are also copy. For example, I32 is copy, but I32 string is not. Ownership and functions. The semantics for passing a value to a function are similar to those assigning a value to a variable. Passing a variable to a function will move or copy just as assignment does. Listing 4-3 has an example with some annotations showing where variables go into and out of scope. Listing 4.3 functions with ownership and scope annotated. If we try to use S after the call to, if we tried to use S after the call to take _ownership, Rust would throw a compile time error. These static checks protect us from mistakes. Trying to add code to main then uses S and X to see where you can use them and where the ownership rules prevent us from doing so. Return values and scope. Returning values can also transfer ownership. Listing 4-4 is an example with similar annotations to those in the listing 4-3. Listing 4-4, transferring ownership of return values. The ownership of a variable follows a simple pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless the data has been moved to be owned by another variable. Taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that we pass in also needs to be passed back. If we want to use it again, in addition to any data resulting from body of the function, that we might want to return as well. The possible return multiple values using a tuple, as shown in listing 4-5. Listing 4-5 returning ownership to perimeters. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for this concept called references. References and borrowing. The issue with the tuple code in listing 4-5 is that we have to return to the string to the calling function so that we can still use the string after the call to calculate underscore length, because the string was moved into calculated underscore strength length. There is how you would define and use calculate underscore length function that has a reference to the object of a particular perimeter instead of taking ownership of the value. First, notice that all the tuple code in the variable declaration and the function return value is gone. Second, note that we pass and s1 into calculate underscore length and in its definition. We take the and string rather than string. These ampersands are references, and they allow you to refer to some value without taking ownership of it. Figure 4-5 shows a diagram. Figure 4-5, a diagram and string equals pointing at string S1. Note the opposite of referencing by using and is differencing, which is accomplished with the difference operator times symbol. We'll see some uses of the difference operator in Chapter 8 and discuss detail of differencing in Chapter 15. Let's take a closer look at the function called here. The AND S1 syntax lets us create a reference that refers to a value of S1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference goes out of scope. Likewise, the signature of the function uses and to indicate that that type of perimeter is S is a reference. Let's add some explanatory annotations. The scope in which variable S is valid is the same as any function perimeter scope, but we don't drop the reference points to it when it goes out of scope because we don't have ownership. When functions have references as perimeters instead of the actual values, we don't need to return the value in order to give back ownership because we never had ownership. We call having references as function perimeters borrowing. As in real life, if a person owns something, you can borrow it from them, and when you're done, you have to give it back. So what happens if we try to modify something we're borrowing? Let's try the code in listing 4-6. Spoiler alert, it doesn't work. Listing 4-6, attempting to modify a borrowed value. Here's the error. Just as variables are immutable by default, so are references. We're not allowed to modify something we have a reference to. Mutable references. We can fix the error in the code from listing 4-6 with just a small tweak. First, we had to change S to be mute, and then we had to create a mutable reference with and mute S and accept a mutable reference with sum underscore string colon and mute string. But mutable references have one big restriction, that you can only have one mutable reference to a particular piece of data in a particular scope. This code will fail. Here's the error. This section allows for mutation, but in a very controlled fashion. It's something that new Rusticians struggle with because most languages let you mute whatever you'd like. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data, or there's no mechanism being used to synchronize across the data. Data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Rust prevents this problem from happening because it won't even compile the code with data races. As always, we can use curly brackets to create a new scope, allowing for multiple references, not just simultaneous ones. A similar rule exists for combining mutable and immutable references. This code results in an error. Here's the error. Phew. We also cannot have a mutable reference while we have an immutable one. Users of an immutable reference don't expect the values to suddenly change out from under them. However, the multiple immutable references are okay because no one who is just reading the data has the ability to affect anyone else's reading of the data. Note that the references scope starts from where it is introduced and continues through the last time that reference is used. For instance, the code will compile because the last usage of immutable reference occurs before the mutable reference is introduced. The scope of the immutable reference R1 and R2 end after the print line, where they are last used, which is before the mutable reference R3 is created. These scopes don't overlap, so the code is allowed. Even though borrowing errors may be frustrating at times, remember that the Rust compiler pointing out a potential bug early at the compile time rather than at the runtime, and is showing you exactly where the problem is. Then you don't have to track down why your data isn't what you thought it was. Dangling references. In language with pointers, it's easy to erroneously create a dangling pointer, a pointer that references a location in memory that may have been given to someone else. By freeing some memory while preserving a pointer to that memory, in Rust, by contrast, the compiler guarantees the reference will never be dangling reference. If you have a reference to some data, the compiler will ensure that the data will never go out of scope before the reference to the data does. Let's try to create a dangling reference which Rust will prevent with a compile time error. Here's the error. The error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in Chapter 10, but if you disregard the parts about lifetimes, the message the message does contain the key to why this code is a problem. Let's take a closer look at exactly what's happening at each stage of our Dangle code. Because S is created inside Dangle, the code of Dangle is finished. S will be deallocated, but we tried to return to a reference to it. That means this reference would be pointing to an invalid string. That's no good. Rust won't let us do this. The solution here is to return the string directly. This works without any problems. Ownership is moved out and nothing needs to be nothing is deallocated. The rules of reference. Let's recap what we've discussed about references. At any given time, you can have either a mutable reference or any number of immutable references. References must always be valid. Next, we'll be looking at a different kind of reference, slices. The slice type. Another type of data that does not have ownership is the slice. Slices let you reference a continuous sequence of elements in a collection rather than the whole collection. Here's a simple programming problem. Write a function that takes a string and returns the first word it finds in that string. If the function doesn't find a space in that string, the whole string must be one word, so the entire string should be returned. Let's think about the signature of this function. This function, first underscore word, has a and string as a parameter. We don't want ownership, so this is fine. But what should we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word. Let's try that, as shown in listing 4-7. Listing 4-7, the first underscore word function that returns a byte value into the string parameter. Because we need to go through the string element by element and check whether the value is a space, we convert our string to an array of bytes using the as underscore bytes method. Let bytes equal s period as underscore bytes. Next, we create an iterator over the array of bytes using the inter method. For colon I, well, here you go, here's this. We'll discuss iterators in more detail in chapter 13. For now, know that inter is a method that returns each element in a collection and that enumerate wraps the result of an integer inter and returns each element as part of a tuple instead. Tuple. The first element of the tuple returned from enumerate is the index. The second element is referred to as the element. This is a bit more convenient than calculating the index ourselves. Because the enumerate method returns a tuple, we can use patterns to deconstruct that tuple, just like everywhere else in Rust. So the for loop, we can specify a pattern that has I for the index in the tuple and the and item for the single byte in the tuple. Because we get a reference to the element from an whatever that is, we use and in the pattern. Inside the for loop, we search for the byte that represents the space by using the byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string by using s.length. We now have a way to find out the index of the end of the first word in the string. But there's a problem. We're returning a usize on its own, but it's a meaningful number in the context of the and string. In other words, because it's a separate value from the string, there's no guarantee that it will be valid in the future. Consider the program in listing 4-8 that uses the first underscore word function from the listing 4-7. Listing 4-8 storing the result from calling the first underscore word function and then changing the string contents. This program compiles without any errors and would also do so if we used word after calling s.clear. Because word isn't connected to the state of s at all, word still contains the value 5. We could use the value 5 with the variable s to try to extract the first word out, but this would be a bug because the contents of s has changed since we've saved 5 in word. Having to worry about the index in word getting out of syntax with the data in s is tedious and error prone. Managing these indices is even more brittle if we write a second underscore word function. Its signature would have to look like this. Now we're tracking a starting and an ending index, and we have even more values that were calculated from the data in a particular state but aren't tied to any state at all. We now have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution to this problem: string slices. A string slice is a reference to part of a string and it looks like this. This is similar to taking reference to the whole string, but with the extra bit. Rather than a reference to the entire string, it's a reference to a portion of the string. We can create slices using a range within brackets to specify where is the first position in the slice, and ending underscore index is more than the last position in the slice. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending underscore index minus starting in underscore index. So the case of let world equal and s 6.11 world would be a slice that contains a pointer to the 7th byte of s with a length value of 5. Figure 4-6, slicing slice referencing to part of string. Stringing slice referencing to part of a string. With Rust's ... range syntax, if you want to start at the index 0, you can drop the value before the 2 periods. In other words, these are equal. By the same token, if your slice includes the last byte of a string, you can drop the trailing number. That means these are equal. You can also drop values to take a slice of the entire string, so these are equal. Note, stringing slices range indicates indices must incur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of your multi-byte character, your program will exit with an error. For the purposes of introducing string slices, we are assuming that ASCII only in this section. A more thorough discussion of UTF-8 handling is in the Storing UTF-8 Encoded Text with Strings section of Chapter 8. With all this information in mind, let's rewrite first underscore world to return a slice. The type that it signifies, slicing string, is written as and str. We get the index for the word in the same way as we did in listing 4-7 by looking for the first occurrence of the space. Then we find a space. We return a string slice using the starting of the string in the index of the space as the starting and ending indicate indices. Now we call first underscore word. We get back to a single value that is tied to an underlying data. The value is made up of a reference to the starting point of the slice and the number of elements in the slice. Returning a slice would also work for the second underscore word function. We now have a straightforward API that is much harder to mess up. Because the compiler will ensure the reference into the string remain invalid, remember the bug in the program in listing 4-8 when we got the index to the end of the first word but then cleared the string so our index was invalid. The code was logically incorrect but didn't show any immediate errors. The problem would show up later if we kept trying to use the first word index with an emptied string. Slices make this bug impossible and let us know we have a problem with our code much sooner. Using a slice version of first underscore word will throw a compile time error. Here's the compile error. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference because clear needs to be truncate the string. It needs to get a mutable reference. Rust disallows this and compilation fails. Not only has Rust made our API easier to use, but it's also eliminated an entire class of errors at compile time. String literals are slices. Recall that we talked about stringing literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. The type of S here is and str. It's a slice pointing to a specific point of binary. This is also why string literals are immutable, and str is an immutable reference. String slices as perimeters. Knowing that you can take slices of literals and string values lead us to one more improvement on first underscore word, and that's its signature. A more experienced Rustician would write the signature shown in listing 4-9 instead because it allows us to use the same function on both and string values and str values. Listing 4-9, improving the first underscore word function by using a string slice for the type of the equals S perimeter. We have a string slice, we can pass that directly. If we have a string, we can pass a slice of that entire string. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. Other slices. String slices, as you might imagine, are specific to strings, but there are more general slice types too. Consider this array. Just as we might want to refer to a part of a string, We might want to refer to part of an array. We do something like this. This slice has type and I32. It works the same way as string slices do, by storing a reference to the first element and a length. You'll use this kind of slice for all sorts of other collections. We'll discuss these collections in detail when we talk about vectors in Chapter 8. Summary. The concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. The Rust language gives you control over your memory usage in the same way as other system programming languages, but having the ownership of the data automatically clean up the data when the owner goes out of scope. This means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work, so we'll talk about these concepts further throughout the rest of the book. Let's move on to Chapter 5 and look at grouping pieces of data together in a struct.